Okay, the first thing we need to talk about here is dependent motion, and as the name suggests, it's when one particle is dependent on the motion of the other. And this is commonly shows up in chords and pulleys, such as what I have here. So the way to deal with this is to determine the position of each moving particle, which would be this pulley here and this block here. Are the two moving particles in this sort of situation. This pulley here doesn't move. So basically I define SB as a position to B, okay, and that's what I need to do is determine the length of each segment. Okay, so I set SB to here, okay, and I set SA going from here to here. Those are the two moving papers, and those are relative to a fixed position. Okay. Then what I need to do is determine the chord length, and it says here exclude the constant segment. Those are kind of highlighted in red, right? This segment over the pulley is always the same length. It's half of the circumference. Same thing up here. This up here is a fixed length as well. It doesn't change in length. And in fact, this H doesn't change in length either. The only things that are changing are SA and SB. Okay, so I can find the chord length just using those and ignoring any of those constant length segments. Once I have that, I'm going to take a time derivative to get velocity and acceleration. That's why those constant lengths can be ignored, because when I take a time derivative of a constant, it becomes 0 anyway. Okay, so you can just ignore those constant limits. And that's how you can relate, speeds and accelerations to things like that. So, next thing we want to talk about is relative motion. Okay, and what we have here is when we have two or more translating frames of reference. Okay, up to this point, basically we're dealing with a fixed frame of reference that we're looking at one particle. Now I may have two particles, each of them moving, and I want to know the relationship between those two. Okay, so for example, I've got two people. Well, I guess here's a fixed observer. I've got another observer here and a translating particle here. So A and B are both moving. This guy's just hanging out at O. That's the origin. That's that fixed point that we typically think about. Okay, but A is moving, B is moving, and I want to know essentially the relative motion between A and B. Okay, so we define position first of all as the position from A to B, and we write that like this. And this basically B/A is the position of B with respect to A. So I'm actually getting B with respect to A. So it's kind of flipped from how we talked about it in statics, where we would write RAB without the slash in there, saying from A to B. We write it B with respect to A. That's kind of how we say that. Okay, so that's the position we're interested in. Which, if I think about vector addition, RA plus R of B with respect to A gives me the absolute position RB, and that's the equation that I have written right here. Okay, and you can always remember how to write this thinking about fractions, right? I've got A in the numerator over here, A in the denominator of the fraction here, cancels out, gives me B. So again, the absolute position of B is equal to the absolute position of A plus the position of B with respect to A. Now, very simply, to find acceleration and velocity, I just take a time derivative, basically changes all of those position vectors to velocity vectors, all those velocity vectors to acceleration vectors. And again, this gives me the velocity and acceleration of one point with respect to another point that is moving as well.